thanks, and thanks for the invitation to speak. I'm also at UCL, but this is the first time I've been to UCL East, so that's also good. So what I'm going to tell you about is some of the AI activities at NPL, which I lead the strategy of. So first of all, question: who's heard of the National Physical Laboratory? Okay, not too bad. So the National Physical Laboratory is the most important institute you've never heard of. Okay, so it's the National Metrology Institute. Okay, not meteorology. That's a different institute. That's the Met Office. We don't predict the weather, although we do actually have climate modelers. So originally set up, I heard today, to measure the concentration or quality of milk. But you can think of us as the people that look after the SI units. Okay, so if you think about timing in financial systems or measurements of kilograms. All of those measurements by calibrated instruments are traceable back to NPL, National Physical Laboratory. So it's the National Metrology Institute, but it's also functioning now as a government laboratory. So we're a company owned entirely by DSIT. If you don't know who DSIT is, it's the Department for Science, Innovation and Technology, who funds UKRI. So we're an arm's length government organisation. We're impartial, so we're generally trusted by industry. And we're set. Our goal at the moment is to really support industry. Okay, so brief overview of AI activities at NPL. We've done a really poor job at advertising what we do. I've been in the job for 8 months, and a lot of my work has been coming out and talking and presenting what we do. So we can split it into 3 areas: Trustworthy AI, AI for science, AI for metrology. We heard a lot about that today, in the materials, for example, and also AI assurance. What I'm going to do is give you a brief introduction into these different areas, the activities that are ongoing at NPL. So Trustworthy AI has been a big focus for the past few years. We got around about 20 papers in the last 2 years in this area. You can think of... Okay, that's not working now. You can think of these different areas for Trustworthy AI. So first of all, you've got software quality. That's building on what we have already. Evaluation metrics, how to go about evaluating AI systems. Data quality and provenance, this is increasingly important. Uncertainty quantification and interpretability. And we've heard a lot about those already today. So I'll just give you a brief run through some of the activities that I thought were relevant today. I should have put some other stuff in now, hearing all the talks, but we do a lot of work on uncertainty quantification. So metrologists are all about measuring things, and associating with that measurement is an uncertainty. So if you don't provide an uncertainty, you haven't made a measurement. Unfortunately, we're not in that situation with AI, machine learning algorithms. In fact, uncertainty really is an afterthought. Okay? And one of the things that's really interesting and what came up today is we still don't really have good methods to handle uncertainty in the training data, right? We don't really have good methods to handle uncertainty in the outputs either. I mean, there are lots of different methods. So one of the things we've been working on is like thinking about how uncertainty propagates through the whole process of training and prediction, building metrology frameworks for uncertainty quantification in models. Oh, wrong way. Different types of uncertainty quantification techniques. So you name it, we've looked at it. Monte Carlo dropout is a common approach. Ensembles, conformal prediction, Bayesian neural networks. We've evaluated all these different approaches to uncertainty quantification. We've looked at uncertainty quantification for generative AI. So particularly in medical imaging, we do a lot of synthetic data generation to increase sample sizes, because in medical imaging you generally have small sample sizes. Plus also style transfer, which means taking, unfortunately, imaging in medical scenario, if you have a different machine, even from the same manufacturer, those data will have different properties. So how you can transfer properties. So here's an example where we've incorporated uncertainty quantification, and you can actually use the uncertainty quantification to identify hallucinations, or errors, I like to call them. Okay, uncertainty disentanglement. So this is trying to, from the uncertainty outputs of your algorithm, what are the sources? So this is a common way to distinguish sources: aleatoric uncertainty versus epistemic uncertainty. Aleatoric uncertainty is due to the stochastic nature of the process and cannot be reduced. Epistemic, in principle, can be reduced. Although what you can see here is a correlation between the two sources. So although people claim they can disentangle different sources of noise, this problem isn't solved, and we need more work to really come up with good methods. Also, uncertainty reliability. Actually, someone presented expected calibration error. We look at different ways to do that. Another aspect I wanted to raise here, because I think it's important for multimodal data, is data quality. There are standards for AI, for data for AI already, 5952 or 5259, ISO 5259. And there are, we should be generating data adhering to those standards. And data quality can mean looking for various different properties, bias and fairness being an obvious one, but there are many different aspects or dimensions of data quality depending on the context. Why it matters, because if the quality of your data is not good, then it propagates into the results of your AI system. And I think if large language models had cared more about data quality, we would see less hallucinations and misalignment. In fact, there's been papers showing that if you clean your data according to certain tasks, then you get less misalignment in your models. Fair and traceable data curation, that's fairly obvious. Semantic technologies I wanted to highlight. We have a team that builds knowledge graphs, ontologies, and we think these are going to be super important for structuring. Well, they're already super important for structuring inputs and outputs to large language models. how agents communicate, defining specifically how information should be formatted and passed, and also for data generation, having these formal descriptions of the data are going to provide trustworthiness, allow you to trace back your data from its sources. Okay, so that's Trustworthy AI at NPL, and I just wanted to talk a bit about now, based on those approaches, how people are using AI for science. So here's an overview of the different areas at the moment. It's probably out of date now, of different areas of science at NPL that are using machine learning and AI. So these are the ones that are involving data science and AI, which is my department, but it's kind of happening in every department. I'm sure everybody can understand that. So I thought I'd give you a couple of slides on some multimodal applications, or what I call multimodal applications. You might disagree. So most of them are in imaging. We do a lot of imaging at NPL across many different types of imaging. So this example here is hyperdimensional image analysis. So mass spectrometry imaging, mass spec imaging. So basically, that's an image where each pixel is a spectra. Okay, so it's incredibly high dimensional. And this is one example where handling that high dimensional data using data reduction algorithms that have been trained, basically, like you can think of it as a t-SNE that's learned using a neural network. So you can do very high dimensional data reduction. And here's an example. Here's the example on hyperspectral imaging. This is a mouse brain segment, and the algorithm was trained on this one in black, and then the other segments. You can see basically the clustering of the data. In light green is glioblastoma. So this allows you to handle much larger data sets with t-SNE like data reduction, dimensionality reduction. Another one that's probably a bit more relevant is combining medical imaging with patient metadata. We showed in a study a couple of years back that combining patient information with the imaging can improve performance. And actually, what you see here in red is a data augmented as well. So we do a lot of synthetic data generation, data augmentation to improve the data sets. But importantly, we try and handle and propagate uncertainty through there. So here you can see basically the improvement of combining these are different metrics here, and here's the improvement with some pre-trained image models. We also do, in a similar vein, this isn't really multimodal, but it's quite cool. Basically, learning representation. So this is kind of segmentation, but what we do is take multiple versions of the same image. Again, it's a data augmentation technique, and this is basically swapping assignments between multiple views, and allows you to do kind of semantic segmentation. So they're interesting multimodal kinds of applications. What I wanted to talk to you today is not really multimodal, but it's cool, so I thought I'd present it. So this is the use of machine learning to define the AMP. Okay, so one of the things we do at NPL is we create those standards that everybody else is going to compare to. Okay, so I'll walk you through this. Okay, so basically all this, if you look up how the SI units are defined, they're all defined now through fundamental constants. And the elementary charge E is how we define the AMP. Okay, I mean that might sound obvious, but in previous incarnations we used proxies. And people are working on single electron pumps. Okay, so these are basically quantum dots, and they're pretty cool. So here's what one looks like, fabricated, and this is how it works. Basically, there's a potential well that's controlled by these two voltages, and if you run this with a certain frequency, so given by VAC here, what you can do by tuning these two voltages is you can have one electron pass through every cycle. So what that allows you to do is define the current like this. So the current, and these are very small currents, the current is defined by N times E times the frequency. Okay, so that's, if N is 1, so we aim for N is 1, so that basically the current is defined by the frequency of this this gate opening and closing. And what you can see here is how it works. So one electron passes through. And this is the plateau here. So if you tune those two voltages, you get this structure like this. So this dark red here, this is one electron passing through the gate for each cycle. This is 2. And you get these mad quantum effects as well, such that 2 go in but 1 comes out. And various interesting things go on. And you can use these to study. So the people in the department who are doing this, they want to study quantum mechanical properties of electrons, because this is a good platform. Anyway, so what we want to do though is scale that. So how do we control these gates? Can we scale that? So for that we've been using, so this shows you why it's useful to have standards here. Allows calibration of things like air quality detectors, optical radiometry, nuclear metrology. So all those detectors that are in everything basically need to be standardized, and that's what we're aiming to do here. Okay. So the goals are to run hundreds of these pumps such that we can generate currents, small currents of arbitrary size. So we want to tune those two voltages, and there's also a magnetic field applied, such that we land on this plateau. So we're operating the quantum dot, we're tuning those two voltages, such that we land in that plateau. And the objective function here, or loss function, is this single electron quantization error. So we've been, work on this previously has used this kind of active learning approach. It's based on a regression with k-nearest neighbors. And what you can see here is cycles of predicting where the plateau lies, followed by data collection. So yeah, you use the regressor to find, you're basically looking for this this plateau here. And what you can see here is the same. So based on the yellow data collected, we predict where to measure next. And that provides a characterization of this plateau, where we want to operate those quantum dots. But we've been extending that approach using a more image-based mechanism. So we have this cycle of point selection. So we want to choose different points in that plane. We use in-painting, so that's predicting the plateau based on those points. And then we have uncertainty quantification in order to choose the next set of points. And we can tune exploration versus exploitation. Again, we only had a small number of images, so we perform data augmentation techniques. What we generally have is a dictionary of transformations that we use, and then we verify the physics that they still are valid. So we augment the data to train the model, and here's what it looks like. So this is the in-painting model. Given those inputs, this is the target, and this is the predicted mean. So just based on those points, we can predict what the plateau looks like. And then we use uncertainty quantification to guide the next set of experimental data collection. This is interesting because this is where splitting your uncertainty up is quite interesting in this case. So the physicists know that the plateau has interesting properties in the middle of the plateau. These are quantum effects. So actually, in order to operate the device, you want to be on the outside of the plateau. So by splitting your variance into the stochastic part, the fundamental noise versus your model noise, this gives you a measure of how much data to collect to improve the model. You can never go beyond this uncertainty because it's inherent to the device. So this allows for different control strategies to be explored, and as I said, also to explore fundamental physics. Okay, so in the last part of the talk, I will talk about AI assurance and the Centre for AI Measurement. So I'm sure I don't really need to describe this because we've got a panel on this after this talk. But for those who aren't familiar, I'm going to go through what AI assurance is and why we need it. So if you talk to companies, which is what we do a lot of, and remember that is NPL's, one of NPL's focuses is to provide support companies and industry. People are very good at producing pilot AI products. But when it comes to deploying, they go to their managers and go, can I deploy? I've built this really cool system. Let's roll it out to the whole of the company. And the manager goes, okay, what evidence can you show me that it's going to work? First of all, what evidence you can show me that it doesn't delete all our data, etc. So assurance is building that trust in those AI systems. Now, assurance can mean a lot of different things. What I'm talking about here and at NPL is test and evaluation, verification and validation, or TEV. Assurance can also mean assuring governance and ethics and things like that, but at NPL we're interested in that, but that's not our focus. It's really how do you evaluate systems and provide evidence that they meet requirements. So why are we doing this? So the government is very keen that the UK becomes a world leader in this. We're already a world leader. Maybe Singapore. Singapore is also could probably claim to be a world leader as well. But the government really wants us to push this because we want AI adoption. So they're predicting that, the market will be £7 billion by 2035. And actually there are 524 firms when they did this supplying AI assurance already. So Deloitte is one. We talk to Deloitte a lot. There are lots of big and small companies that offer third-party AI assurance. A lot of those won't be doing technical. My estimate is about 200 of those are doing technical AI assurance. So what is the challenge? So, well, we're having a panel on it today, but science and tooling gaps, quality infrastructure. The market is early, so it's fragmented. Lots of different methods are being used. It's a bit like the Wild West. So there's a lot of work to do in terms of unifying it, and that's why NPL is involved. So we have been working on AI assurance at NPL for a number of years, so I won't have time to talk about it, but we've done a lot in healthcare systems. We've worked with hospitals and NHS trusts, autonomous systems, so land, sea and air. So we have a program on autonomous systems and also biometrics. So, for example, you may have seen us mentioned on measuring and evaluating facial recognition systems that police forces are using, and we found them to be biased, unsurprisingly. Okay, so out of that we have developed a framework. This is not really for assurance, it's for developers and deployers. So it's called the Trustworthy and Safe AI Lifecycle, and it's actually built on it's built on the NIST AI risk management framework. We tried to operationalize it. So essentially, all of these approaches are converging on a risk analysis. The risk assessment is done with experts, so a collaborative set of experts, and then it shouldn't be called risk analysis. It should be called risk benefit analysis, because you have to take into account the benefits, and then you map those down to things that you can measure. Okay. And that's where the measurement comes in, and you evaluate the system. Another very important thing that I shouldn't forget is that this is a life cycle. So we don't develop and then deploy. We have to develop, deploy, and monitor. Okay, and that monitoring step is going to become more and more key to getting AI systems out into the real world. So what is measurement? I mean, maybe I should have said this at the start, but measurement is this process of experimentally obtaining a quantity of values that can be attributed to a quantity. And you can look up, there's lots of documentation that Metrology is based on that were agreed over many years. And and there's a long history of work in this area. So why do we need measurement for AI? So we need to ensure trust and safety of AI. We need to be able to communicate with each other, like particularly vendors who are selling products, procurement teams. There needs to be objective language that can be understood by everyone. And measurement helps us to compare and assess different algorithms. So the government, or DSET, has funded us to start this Centre for AI Measurement. So this was begun in April, so it's quite early, and that's to build confidence in AI by improving the science of AI measurement. And there's three aspects to that. So there's research and development. So this is the part that I lead. So this is collaborative research and development in AI, test evaluation, validation, and verification. Industry support programs, so that's working with third-party assurers, working with deployers, trying to assure the systems and improve uptake. And then also an AI assurance innovation network. And we want academics involved. We will produce a booklet, like a problem book, which is like, what are the challenges? What should academia be helping us with? And hopefully we can build the methodologies to improve adoption. So here's my viewpoint of a very complicated, it's super complicated system. But it's very similar to how other regulation is done. So here, these are the test and evaluation companies. These are developers and deployers. You might have different sectors. You might have different sector-specific requirements. Regulators will maybe set standards, and then UCAS are the people who accredit the test and evaluation companies. So what we're doing is we're trying to underpin that structure, provide the methodology, provide the language for everybody to communicate, and provide a foundation for this. So the way we're going to do that is this protocol approach. So in metrology, we often have a measurement document of how to perform a measurement. So it might include information on the machine, the conditions, when it does apply, when it doesn't apply, and a step-by-step process. So we're going to do the same for AI test and evaluation. So we're going to operationalize this into a toolbox of protocols. And this provides some form of traceability. So traceability means you can attribute some property to your AI system. And what I like about this as well is that somebody selling a system can say they used NPL protocol XYZ on this data and achieved this result, this performance accuracy, say. And that is a verifiable claim empirically. So another important thing is these are pre-standards, so we will update them. They form a hypothesis as to what is the best practice or the good practice right now, and they're also hierarchical, so they build on each other. So different protocols that we're planning and going to work on. So as you can imagine, uncertainty quantification, data quality, and I think both of those are important for multimodal data applications, interpretability, all the things I mentioned, AI semantics. So how do we structure the frameworks around language models and agents, Bias and fairness we already do a lot of, and then this idea of post-deployment methodology. So if you're interested in researching any of these things, please come and chat to me. And then just to say, you know, we will work towards standards. This is a slower process. We're involved in the AI Standards Hub with BSI, Turing, UCAS. And this is to, and I guess in the future, the protocols that we've developed will eventually become standards, hopefully. So that's the end of my talk. I think this is super important for multimodal applications. If we want to get them out into the real world, we need to work out what methods to use, the benchmarks and metrics, and how to monitor them after they've been deployed. So thanks.
Thank you very much, Chris. I was great to see the Lord Kelvin quote there. I do like that quote. I'm ex-NPL myself, and good to see an ex-KCD cartoon. No day is complete without one. Any questions?
Great talk, thank you. I've got a question regarding processes and governance at NPL. What is your stance on your researchers using agentic coding agents?
Okay. Yeah, so good question. In fact, I'm in let's not call it a fist fight, but we're not allowed to use them right now, is the simple fact. NPL has a lot of processes around coding, code quality. Everything has to be audited by someone. We have something called Ticket Plus. I don't imagine any of you have heard of that. This is a standard for writing code. So we are working towards using agentic coding, but that is very, very cautiously moving in that direction.
So does it vary from researcher to researcher? For example, some projects are allowed, some are not, or it's banned, basically?
It's banned. Apparently, this is before I joined, I've only been there 8 months. Somebody uploaded a load of sensitive code into ChatGPT, and then that put a blanket ban on anything. But there are sensitive applications, but not everything's sensitive. So, you know, metrology is... The reason people trust metrology is because it moves slowly and is very meticulous. So, yeah, the challenge is how do we adapt metrology for the AI boom? So, yeah, but it's a good question, and it's something I want to get, you know, people using a bit more, yeah. I should say, we can use it, but we're only allowed local models.
Have you got your own local hosting platforms then?
Well, we've got a small cluster of GPUs, but, you know...
And you have your hosting platform there?
Well, we just run our own All-Llama model and use it in VS Code, for example. So we're allowed to do that, yeah. We're just not allowed to use Claude Code yet.
Just a follow-up, what about like formal verification? Are you using formal verification?
Very good question. Not at NPL. It's not something we have the skills or we're built up for. So working with academics, we would want to do more of that. The question was about formal verification, but it's still an open area. You know, it's not solved for AI systems. But eventually, for a safety critical system, you would want formal verification. Yeah, for sure.
We'll go that side, then we'll go.
Thank you. Great talk. Thank you. I have a question about when you mentioned working on AI assurances with hospitals. And one of the things I've observed with hospitals is that there's lack of resources for supporting AI deployment. So has that been a challenge? And if not, what are some other challenges that you've faced?
Yeah, good question. So that is one of the biggest things I think is a barrier to deployment, is actually the infrastructure that's needed around it and people underestimating that. So there is a standard for the system around your AI system. It's called ISO 42001. Has anyone heard of that? One, okay, or two. Yeah, so that, you know, if you adhere to that standard, it means that you've had to have gone through and put all those processes in place. So we definitely see that people underestimate what is required to deploy and provide auditable material, auditable. In terms of other things, I think another big challenge in medical scenario is we have no idea how images are being processed, right? It's all proprietary. People update firmware and the image changes. So actually the post-deployment stuff we did with Royal Marsden was actually monitoring performance over time as the equipment received firmware updates. So I think that's a big challenge, and we have no access to the underlying. There's already AI sneaked into those image analysis platforms. Same with on your phone. You know, if you take a picture on an iPhone, you know, it's more than likely been cleaned up with an AI algorithm, and they've sneaked in somehow under the radar into all this kit. And I think that's another big challenge.
You mentioned earlier how important it is to clean your data. And my question to you is, personally, what would you say the line is between cleaned data and unrealistic synthetic data? For example, if you're working on a small data set, like protein sequences, you can't really augment too much because now you're disobeying the rules of biology. Or if you leave out certain sequences to try maybe remove missing data or incomplete data, you're not getting a realistic approach to the field when you're actually running with realistic data. So I wanted to ask you, like, how do you guys draw the line to be like, okay, we can manipulate this data to a certain extent, but not make it unrealistic or make a virtual biased model? Or
Very good question. And if you do it, I'm not saying we've solved it, but in principle, if there is a calibrated uncertainty associated with your synthetic data, then the synthetic data that is far from the real distribution will have larger uncertainty, and that should propagate into your training, you know, just as it would do if you collected data and, you know, in certain conditions where your instrument doesn't have a good precision. That should propagate, but that's not really being done, as far as I understand, in routinely. Because we don't really have the algorithms that can take a point and an uncertainty. I mean, you can build you can double up the inputs to a neural network, but, you know, you still have to calibrate it on other data, you know, on a calibration set. But in principle, uncertainty can help you there.
Last question of me is as chair's privilege. So, as mentioned, I used to be at NPL as well, and as you mentioned, metrology moves slowly, and people are quite conservative. How have the humans taken on embracing ML and AI in various parts of metrology? Are they very scared of it, sceptical of it? What's the sort of almost the politics of it?
Yeah, so actually one of my questions in my job interview was that. And because I imagined it would be very, you know, met with, let's say, caution. So I'm a particle physicist, originally. And when I was doing particle physics, they were purely frequentist, right? They would not use Bayesian statistics. And I was expecting that kind of reaction, but it's not. People are using it, as I showed there for the quantum example. People are using less so language models, but people are moving that way. But people are wanting to use it, and we're just slowly allowing them to use it.
Great. Thank you very much, Chris. And please can we thank Chris again?